Military systems are designed around assumptions, not through dishonesty and not through incompetence, but because the people who write specifications must define conditions in advance, and assumptions, by their nature, describe the world as it is expected to be, rather than the world as it actually turns out to be. In the summer of 1943, somewhere over the industrial regions of Germany, a discrepancy emerged between those two versions of the world. On one side was a carefully designed defensive system, built to precise tolerances, tested thoroughly, documented in official manuals, and issued with complete confidence to the men responsible for operating it. On the other side were the operational conditions encountered at altitude, an opponent that had studied the system just as carefully and learned through methodical experience exactly where its limits were. This video is presented for historical and educational purposes only. The story of what followed does not appear prominently in official summaries of the air war over Europe. It is the kind of episode preserved in after-action documentation, engineering correspondence filed under administrative reference numbers, and technical discussions that rarely moved beyond the units involved. Yet the consequences of what occurred are still visible today in how defensive systems are designed and in a principle now treated as self-evident: response speed is not a secondary consideration. It is fundamental. To understand the problem, it helps to examine the machine at the center of it. The Sperry ball turret was one of the more technically sophisticated components produced for the American war effort. Designed to occupy the most exposed position on the B-17 Flying Fortress, suspended beneath the fuselage in a sphere of aluminum framing and curved plexiglass, it provided a single operator with coverage of the lower hemisphere surrounding the aircraft. 2.50 caliber machine guns extended forward through the turret's face. The entire assembly could rotate through a full 360 degrees of traverse and elevate through a wide vertical arc. On paper, it addressed one of the fundamental vulnerabilities of large bomber formations: approach from below. The operator sat with knees drawn upward, positioned close to a computing gun sight, hands on control grips that directed the turret through an electrically driven system. Push the grip forward and the guns elevated. Pull back and they depressed. Rotate left or right and the entire sphere followed. The system was smooth, consistent, and engineered to a defined standard that planners had determined represented the optimal balance between speed and control. That standard was a traverse rate of approximately 30 degrees per second. At that speed, a trained operator could track a fighter making a conventional approach, calculate the necessary deflection, and respond in controlled bursts. Engineers had evaluated the physics carefully: turret mass, available motor torque, mechanical stresses associated with rapid movement, and deliberately incorporated a governor assembly into the control system. This device, a calibrated arrangement of spring-loaded friction plates, moderated control input to prevent abrupt motion that could introduce oscillation and reduce accuracy. The logic was sound within the environment that had been modeled. The difficulty was that the environment did not remain static. The German air defense system that American bomber crews encountered over Germany in 1943 had evolved through extended operational experience. Years of sustained air operations against multiple opponents had produced refined interception methods based on observation, timing, and coordinated positioning. Analysts had examined the bomber's defensive layout carefully, identifying where its coverage was strongest and where mechanical limits imposed delays. The key insight was straightforward. If the turret's maximum traverse rate was fixed, then the limiting factor in any engagement was the time required to reposition it. A single aircraft approaching from a predictable direction could be tracked effectively. Multiple aircraft arriving from separated bearings created a sequencing problem the system was not designed to solve quickly. By the time the turret transitioned from one position to another, the geometry of the situation had already changed. Interception tactics evolved to take advantage of this interval deliberately. Coordinated approaches from multiple vectors became standard practice. Elements would arrive at carefully spaced moments, forcing operators to prioritize one direction while another fell within the response delay created by turret rotation. It was not improvisation. It was a measured application of timing against a known mechanical parameter. To the crews involved, this appeared not as an abstract tactical problem, but as a recurring operational pattern. A measurable delay between successive engagements, an observable response cycle within the mechanical system, and the recognition that this cycle could be anticipated externally. Debriefings and informal discussions returned to the same observation. The turret was functioning as designed, but the margin built into the governor assembly, intended to ensure smooth tracking, imposed constraints under these specific conditions. The official interpretation remained consistent. The turret met its specifications. Traverse speed fell within established tolerances. Engineering analysis supported the original design balance. What units were observing was attributed to the evolving nature of air operations rather than to an equipment deficiency. This assessment was technically accurate, but it did not address the mismatch between specification and experience. The adjustment that eventually altered this balance did not originate in a formal study. It began with maintenance personnel examining the mechanism directly and recognizing that a change in calibration might alter system behavior. The governor assembly itself was mechanically straightforward. Its purpose was singular: to limit how rapidly control input translated into motion. Its components were accessible to technicians accustomed to tracing mechanical linkages in confined spaces. What followed was a decision to adjust the equipment outside the formal engineering revision process, implemented during routine servicing rather than through official modification channels. The earliest documented instance within 8th Air Force units dates to late spring 1943. Accounts differ in detail, but the essential action was consistent. Maintenance crews accessed the turret's control system, located the governor assembly, and reduced, not removed, the spring tension acting on its friction plates. The intention was not to eliminate dampening, which would have introduced instability, but to recalibrate the balance point, accepting slightly less smooth motion in exchange for faster response. Subsequent missions demonstrated a traverse rate roughly 30 to 35% faster than the original specification. The turret retained sufficient stability for accurate operation, but the time required to shift between bearings, the response interval those tactics had been structured to take advantage of, was significantly reduced. What followed illustrates how practical knowledge can circulate when formal pathways are slower than operational demand. The adjustment moved through maintenance channels in an informal but technically specific way. A crew chief observing altered performance discussed it with another unit. Operators compared response characteristics. The technical details circulated alongside observed performance differences, what had been adjusted, how it was done, and how the system behaved afterward. Some crews adopted the change, others did not. There were no written directives and no centralized coordination. By midsummer 1943, Several dozen aircraft across multiple groups were operating with governor settings that differed from their documented configuration. The information remained deliberately localized, below the level of formal reporting. Operational effects were noted from multiple perspectives. Within American units, aircraft incorporating the adjustment began generating reports that differed from earlier patterns. Engagement sequences that previously fell within the turret's response delay could now be addressed more quickly. Approaches, based on predictable timing, encountered defensive reactions earlier than expected, requiring changes in geometry or premature disengagement. From the opposing side, pilots reported encountering defensive systems whose reaction times varied from established expectations. The aircraft appeared unchanged externally, yet their behavior differed in ways that could not be easily categorized. Because the modification left no visible signature, it was difficult to analyze systematically. This ambiguity helped preserve its effectiveness. An alteration that could not be identified externally was harder to counter through observation alone. The official discovery of the adjustment resulted not from combat events, but from routine technical inspection. Engineering teams conducting evaluations identified governor assemblies whose calibration did not match specification. The deviations were consistent and directional. All increased traverse speed. A formal review followed. The investigation highlighted a familiar institutional tension. Changes had been applied outside documented procedure. From an administrative standpoint, this created questions of compliance, liability, and precedent. Yet engineering evaluation of the modified assemblies produced measurable findings. Increased traverse speed matched field observations. Accuracy degradation was present, but acceptable. Mechanical analysis indicated no significant increase in system stress or failure risk. The evaluation concluded that the field adjustment addressed a legitimate operational mismatch. The original specification had been developed against assumptions about engagement patterns that experience had not fully supported. The recalibrated governor shifted the balance toward response speed in a way that better aligned with observed conditions. Administrative responses reflected this mixed picture. Procedural violations were acknowledged, but the institutional focus moved quickly from enforcement to integration once the technical validity was confirmed. Formal adoption proceeded through wartime engineering channels. Technical orders were revised. Production drawings were updated. By early 1944, newly manufactured aircraft incorporated governor settings aligned with the empirically derived configuration. Retrofit kits followed for aircraft already in service. Official documentation attributed the change to engineering review and field evaluation. The informal pathway through which the insight first emerged was compressed into standard technical language. This was not unusual. Large organizations often absorb decentralized solutions by translating them into formal specification. Once they are validated, the broader significance lies less in the specific component than in the process it illustrates. The original design had been produced by capable engineers working from reasonable projections. The opposing system adapted its methods in response. Operational personnel then adjusted the equipment to restore alignment between design intent and actual conditions. Institutional mechanisms eventually captured, validated, and standardized that adjustment. This sequence: assumption, observation, informal correction, represents a recurring pattern in wartime engineering environments. The knowledge most immediately tied to system performance is generated at the operational level. Formal processes follow afterward, translating localized insight into consistent practice across the organization. The B-17 ball turret is now primarily encountered in museums. The aircraft themselves no longer fly. The technical orders governing their maintenance exist as archival material consulted mainly by historians and engineers, studying earlier design approaches. Yet the principle reinforced during this episode did not remain confined to a single aircraft. Later defensive systems across air, sea, and ground incorporated response speed as a primary parameter from the outset. Designers increasingly treated reaction time not as a secondary refinement, but as a defining characteristic to be evaluated alongside accuracy, durability, and range. The episode demonstrates how complex organizations adapt under pressure. Systems are conceived centrally, but they are refined through continuous interaction with the environments in which they operate. When those environments shift, successful institutions are those able to absorb feedback, whether it originates in formal analysis or an incremental adjustment, and translate it into durable specification. What remained was not a story recorded in detail, but a revised standard, and standards once integrated tend to outlast the circumstances that first required them.